Yeah, Assalamu alaikum. This is your Thermodynamics 2 class, and today is lecture number 26. So, can anyone confirm what's appearing on my screen right now?
Walaikum
In
assalam,
this
sir.
introduction slide, lecture 26. Okay, thank you so much. Okay, so as it is mentioned again, it is from compressible flow. Okay, so before starting the lecture, I will just correct something that in your book or in the previous lecture, because I have just copy paste this figure and there is something wrong with this figure. That here it is mentioned supersonic nozzle. Okay, so it is basically diffuser. This is diffuser and this one is nozzle. Okay, so you have to correct these two thing in this figure. Okay, and rest of the thing is the same. Okay, because I have just copy paste this figure and I have noticed after it that there is something wrong. Okay, so starting from the chapter 17 again, so we will try to solve some more examples related to converging diverging nozzles or converging nozzle or diverging nozzle. Okay, so here it is 17-58 from your book. This problem is that air enters a nozzle at 0.2 megapascal. Temperature is given, velocity at inlet is given. Assuming isentropic flow, and you have to determine pressure and temperature of air at location where the air velocity equal to speed of sound. And what is the ratio of the area at this location to the entrance area? So this is the question, and from this question you can easily judge that, for example, if this is your nozzle, and at which location your Mach number become equal to 1, or you can say air velocity equal to speed of sound. So this is the area, so we can call as a throat area. Okay, I already told you that in this area, which is your outlet, so here there is the Mach number equal to 1. Okay, so our main target is to find, you can say P star and T star. And inlet properties are given, that your pressure is given, you can say Pi at the inlet, which is 0.2 megapascal. Temperature at inlet is given 350 Kelvin. Velocity at inlet is given 150 meter per second. And inside there is air. And another thing which we want to find is what is the ratio of the area at this location to the entrance area. So it's mean we are interested in to find A star over A. So A star is at this point and area is at this point. So this is also we have to find. This is your question. So you have to note down the data and then we will see how to solve it. Okay, so we will start uh, the same slide. Okay, so as we have to find P star, T star and A star, and you already know that if you want to P star, T star or A star, that is the critical properties, we have to find first stagnation points or stagnation properties. Okay, so first thing, in order to find P star, we need to find the stagnation pressure, and in order to find T star, we need to find the stagnation temperature. So first thing is we can find stagnation temperature. The stagnation temperature is equal to Ti minus Vi square over 2 Cp. So Ti is known to us because it is at inlet. Vi is known to us. So simply you have to plug in all the value and you will get the T naught. So T naught is 350 minus 150 meter per second square, and then 2 into 1.005, and it is in kilojoule, so you have to convert into joule. So if you can solve it, you will get the T naught easily, which is 361.2 Kelvin. So from T naught, we can easily find the P naught. So P naught by using the isentropic relation. So P naught is equal to Pi T naught over Ti K divided by K minus 1. So we have T naught with us from the previous part. Ti is known to us, Pi is known to us, and specific heat pressure for the air is already known to us. So simply you have to plug in all the value and you will get your stagnation pressure, which is 361.2 2 T naught value, T1 value is 350, and 1.4 divided by 0.4, and if you can solve it, you will get the P naught as 0.223 megapascal. So now we have P naught and T naught with us, so we can easily find out P star and T star from the relation we already know. So you have to note it down, and then we move towards the next part. Okay, so now for P star by P, you already know the relation that P star by P is equal to 2 K plus 1 K minus 1, and T star by T, which is equal to 2 y by K plus 1. So by simply putting all the values, that is K value, so you can get the P star by P ratio. Or also you can get this P star by P value from the thermodynamic table. So if you can quickly go to thermodynamic table 832. So against this mark number 1, because T star by P mean that we are interested in mark number 1, that is the critical point. So from there you can find that P star by P value is 0.5283, and T star by T naught value is 0.8333. Okay, so we can directly find these value from the thermodynamic table as well. So I will just write down the value. So P star by P is equal to 0.5283, and T star by T is equal to 0.8333. So, and this is your stagnation point, which is P naught and T naught. So from here we can find P star as 0.5283 multiply P naught we already find in the previous step, which is 0.223 megapascal. So from here we get the P star, which is equal to 0.118 megapascal, and similarly we also find T star, which is equal to 0.8333, and multiply by your stagnation temperature, which is 361.2, and here we get the T star as 301 Kelvin. So now these two parameters which is required in the problem statement, that we have to find pressure and temperature at the location where air velocity is equal to speed of sound, is known to us. So now we are going towards the next part, which is to find A star by AI. So for this, either you can use direct formula, which we already know that there is some formula which relate A star by A. Okay, so for that we need the Mach number first. And next procedure is, you can easily, if you find the Mach number, you can easily go to thermodynamic table 832 and find that ratio against that Mach number. So I will just find the Mach number first. So for Mach number, so you can say that Mach number at inlet, which is equal to V inlet or C inlet. So V inlet is known to us from the problem statement. It is 150 meter per second, and C inlet we have to find. So C inlet is basically under root KR TI. So you can plug the value, K value 1.4, R value is 0.287, 1000 for the conversion factor, and then your TI which is equal to 350, which is mentioned in the problem statement. And if you can solve it, you will get the Mach number, which is equal to 0.4. Okay, so now we have the Mach number at inlet. So simply what you have to do is either you can plug the values into the formula, which we already know, or either you can go to thermodynamic table and find the value against it. Okay, so this is the A by A star formula, which is mentioned over there. So this formula, you can just plug the value and you will get it, or either you can look into 0.4. So it's a Mach number, and our A by A star value is this one, A by A star, and here we have 1.5901 is the value. Okay, so simply you have to write down the value that A by A star. So this is AI basically, and it is equal to 1.5901, and the required thing is to find A star by AI, because it is clearly mentioned that the ratio of the area at this location to the entrance area. So at this location means where your Mach number is 1. So A star by AI is equal to 1 divided by 1.5901, and which is equal to 0.629. So this is the required solution for this problem. If you have any question, you can ask me, or you can note it down. Okay, so here this is the next question. This is example 17-7 from your book. So first you have to read the statement. Air enters a converging diverging nozzle. The figure is shown over there. At pressure is given, temperature is given with a negligible velocity. So it's mean that is the stagnation temperature and stagnation pressure is known to you. The flow is steady, one-dimensional and isentropic. That K value is known to you. For an exit Mach number of 2 and a throat area of 20 centimeters square. So you have to determine the throat condition and exit plane condition, including exit area, and C part is to find mass flow rate to the nozzle. Okay, so this is the required thing. Okay, so what is the meaning of throat condition? As I already told you, that throat mean in the converging diverging nozzle, the area where your Mach number is equal to 1, and the properties that are related to this area is related to as P star. So throat condition means we have to find P star, T star, rho star, and velocity star at the throat area where the Mach number is 1. And now the exit plane condition mean we have to find something properties that is related to the exit point. So P exit, temperature exit, density exit, and velocity exit. And also it is clearly mentioned that you have to find the exit area as well. So area exit as well you have to find. Then mass flow rate through the nozzle. So mass flow rate, you can easily figure it out. Okay, so as it is clearly mentioned that the area is mentioned at the throat, so you can find the mass flow rate at the throat point, and because it is a steady flow, so it's mean that the flow that is coming in is same throughout that converging diverging nozzle. So for mass flow rate, you can find out at the throat point. Okay, so you have to note down the data and then we will see how to solve it. Okay, so starting from the first part, so in part A, our main target is to find P star, T star, rho star, and V star. Okay, so in order to find P star, we need the stagnation pressure. So stagnation pressure is known to us from the problem statement. For finding T star, we need to find T naught. So T naught is also mentioned, but in order to find rho star, that is critical density, we do not have the rho naught value. So first thing is we have to find the rho naught. So in order to find rho naught, so simply you have to use ideal gas relation, which is rho naught is equal to P naught R T naught. So if you can simply put the value, so P naught is 1 megapascal, so you can say 1000 kilopascal. R value is 0.287 and T naught value is 800 Kelvin. So if you can solve it, you will get the rho naught value as 4.355 kg per meter cube. So now rho naught value is known to us. So simply either you can use the formula which we already know, that P star by P is equal to 2 divided by K plus 1, K divided by K minus 1. Similarly, T star by T naught, which is equal to 2 divided by K plus 1, or rho star divided by rho naught, which is equal to 2 divided by K plus 1, 1 K minus 1. Okay, so you can use these formula, or simply you can go to table 832 and against mark number 1, you can find out P star by P naught value. Okay, so in a similar procedure which we already did in the previous example, 0.5283, T star by T naught value, which is equal to 0.8333, and rho star by rho naught value, which is equal to 0.6339. So now these properties are known to us, which is the ratio of T star by T naught and all the stagnation properties. So from here we can easily figure it out: P star, T star value, rho star value. So P star value, which is equal to 0.5283 into P naught. So P naught is 1 megapascal. So you can find out that P star is 0.5283 megapascal. And similarly T star, which is equal to 0.8333, and you have to multiply T naught, so which is 800 Kelvin, and which is equal to 6.6 Kelvin, and rho star value 0.6339, and you have to multiply stagnation density, which is 4.355, and you can find out the value, which is at 2.761 kg per meter cube. So rho star value now known to us. So the last thing is to find V star. So as it is mentioned that V star at the throat area, your V star is equal to C star. Okay, because Mach number is equal to 1, so you can say that it is equal to Kr T star. Okay, so K value is known to us, R value is known to us, and T star value you already find on this step. So simply you have to put the value. So it is equal to 1.4, 0.287, 1000 for the conversion factor, and 666.6 value is the value for T star. So from here your V star become 517.5 meter per second. Okay, so all the properties that is related to the third condition you already find, which is P star, rho star, and V star. Okay, so this is the required solution for part A. You have to note it down, and then we move towards part B. Okay, so in part number B, we have to find exit plane condition, which is P exit, rho exit, velocity exit, and area exit. Okay, so in order to find this, simply you have to go to, because Mach number is known to you, so you can easily find the ratio of P by uh, P naught, T by T naught, rho by rho naught, V by V naught, V exit A by A star. Okay, so these value you can easily figure it out from the table A32, because Mach number is already known that at the exit Mach number is 2. So for the 2 condition, you can find the value of A by A star, P by P naught, rho by rho naught, T by T naught, and basically this is at AE, this is P exit, this is rho exit, and this is T exit. Okay, so you have to note down these values from this table, and now I'm going to just write the values. So P exit over P naught, which is equal to 0.1278, T exit over T naught, which is equal to 0.556, P exit over P naught, which is equal to 0.2300, and area exit over area star, because this is the property which is mentioned, 1.6875. So by using these relations, we can easily find out the value of P exit. The P exit is equal to 0.1278 into P naught value. So P naught value is 1 megapascal, and it is equal to 0.1278 megapascal for P exit. T exit, which is equal to 0.556, and your stagnation temperature is 800 Kelvin. So multiplication, you will get 444.5 Kelvin, and you have to find the rho exit as well. So rho exit is equal to 0.2300 into 4.355, and which is equal to 1.002 kg per meter cube. So now we have to find area exit. So area exit is equal to 1.6875 into area star. So area star is given in the question, which is 20 centimeters square. So if you can multiply, it will be 33.75 centimeters square. So now the last thing which is required is that is V exit. So V exit basically equal to Mach exit into C speed of sound at exit. So Mach exit is known to us. The C exit we can easily find out because temperature exit is known to us. So Mach exit to multiply under root 1.4 value of K, R value 0.287 into 1000 for the conversion, and then T exit is equal to 444.5, and if you can multiply you will get the velocity exit as 845.2 meter per second. So exit plane condition are now known to us. Okay, so this is the required solution for part B. So you have to note it down, or if you have any question you can ask me, otherwise we can solve part C as well. So part C is basically very simple because we uh, know the area star. Okay, so you can find out mass flow rate, and it's also mentioned it is a steady flow. So you can find at the throat area. So mass flow is same. So rho star area star into V star. So rho star value 2.761. Area star is mentioned in the question 20 to 10 raised to power 4. You can convert into meter square, and V star value is 517.5, which come from part A. So from there you can find out your mass flow rate, which is 2.86 kg per second. So this is the solution for part C. So you have to note it down. Then we move towards the next question. Okay, so coming towards next question, and this is not from your book, so you have to note down the data first. So airflow isentropically through a duct. So they mentioned that it's a converging diverging nozzle basically, or you can say duct. At section 1, the area is 0.05 meters square. Velocity at section 1 is known to you. Pressure at 1 is known to you. Temperature in section 1 is known to you. You have to compute stagnation temperature, Mach number at point 1, stagnation pressure, both A star and M dot. Okay, and this statement has not linked with this problem. Okay, so you just have to eliminate it. Okay, so this is the figure. So you have to note it down or draw the figure, and then we will see how to solve it. Okay, so here the first part, so part A, we have to find the stagnation temperature. So as we already know the V1 and T1 value, so we can easily find the stagnation temperature by using this relation. T naught is equal to T1 plus V1 square divided by 2 Cp. So T1 is known to you, V1 is known to you, and Cp value for air is already known to you. You just have to simply put the value which is equal to, and I'm just going to write the answer which is 486 Kelvin. So this is the part A solution. So part B, we have to find the Mach number 1. So at section 1, we already have T1 value, and also we already know the V1 value, so we can easily figure it out the value of Mach 1, which is equal to V1 over C1. So V1 is 180 and C1 is under root K 1.4, R value which is 287 in Joule, and T1 value which is equal to 470 Kelvin. So from here we can easily find the Mach number at 1, which is 0.414. So this is the solution for part B. So solution for part C. So in the part C, we have to find the stagnation pressure. So stagnation pressure, you already know the relation P naught divided by P1 is equal to 1 plus K minus 1 divided by 2 Mach square K divided by K minus 1. So simply you need to put the value of Mach and K value, specific heat ratio for A, and P1 is already known to you from the problem statement. So you can find easily P naught. So P naught is equal to 563 kilopascal. So this is the solution for part C. So in coming towards part D, so for part number D, we already know the relation that A by A star, which is equal to 1 over Mach 2 divided by K plus 1, 1 plus K minus 1 divided by 2 Mach square. So this relation we already developed in the previous lecture as well. So simply you have to plug the value of Mach number because that is known to you, and then K value, and this area is already known to you from the problem statement that this area is, you can say area at 1 is equal to 0.05 meter square. So from this relation you can easily find out A star value. So A star value, which is equal to, I'm just going to write the answer, you have to plug the value and find out the 0.0323 meters square. So this is the A star. So as also we have to find the mass flow rate. So mass flow rate at the throat, which is we know that at the throat it is the maximum mass flow rate. So simply you have to apply the relation. We already know that mass flow rate maximum, which is equal to A star P naught under root K R T naught to K plus 1 divided by 2 K minus 1. So by using this relation, A star is known to you from the previous step, P naught is known to you, K value known to you, T naught known to you. So all the things are already known to us. So simply you have to put the value, and the mass flow rate become 3.4 kg per second. So this is the solution for this type of problem. So if you have any question, you can ask me, or you can note down, or we can just stop at this point.
सर ये नीचे वो ब्लैक बार है वो काइंडली जरा हटा देंगे लिखें थैंक यू सर
Okay, so we will stop at this point, and the question which you have to solve is the same one. So just you have to make it 0.04 meters square, and rest of the procedure you have to do it by yourself and send it to me. Okay, so you have to note it down, and I will just stop at this point. Another important thing is that I have just uploaded all the result in the Kalam, or you can say in the Odoo. So you can access these results of your quizzes and assignment, whatever you have sent it to me from the coming Monday, because at this time the visibility is off. So I will turn on the visibility on Monday, so you can check your result. If you can find anything that it is not correct or something it is missing, so you can contact me. I will go through it again.
ओके सर ये सेक्शन 1 का एरिया 0.05 से 4 कर दें।
जी 0.04 मीटर स्क्वायर कर दिया।